And as you can see, how the filings are following it around, and that is why our planet is actually always drawn upside down. It's pretty interesting. Yeah. Oh, hey, so we're gonna go over what I was just talking to Mr. Bones about before we started this video, but you kind of caught me right at the end of our practice. So today we're gonna be discussing week 18, electromagnetism. So got a little lightning bolt and some arrows, and you're like, what's up with that? Well, if you remember way back when, I think it was week 3 or 4, we were discussing the 4 fundamental forces of the universe and how they make everything possible. And then we went a little in depth into each one. And today I wanted to come back to electromagnetism, especially that magnetism part of it. So electromagnetism is a field of force, 4 fundamental forces, that's created by the flow of electric current. Now we use electricity for everything in the modern age, and it's just going to become more and more prevalent in every single thing we do. So maybe we should understand how it interacts in our world, and when we're talking about frequencies going through the air and being invisible, that's electromagnetism. We can't see it, but it affects so much of our world. So on a magnet, which is very similar to the ones we usually have in class, you'll notice that I've kept the colors the same. There is a negative side and a positive side. Now the negative side is usually where there's a whole bunch of those electrons. And if you remember, we were talking about, I believe electrons were a lepton. They're one of those subatomic particles, and there'll be a ton of them just waiting over here to go somewhere. And the other side will be positive, waiting to accept those electrons and say, hey, we have space for you, come on over. So the electrons, you'd think, could move through the metal, right? They could just keep going through, but it's actually harder for them to move through here than it is to just jump outside real quick and come back over here. So that motion of the electron moving from one area to another causes a small field to be generated. And it's not a field we can see like we kick and play on, but it's more like a little energy area, just an area of energy that happens. And the closer you are to where those electrons are moving back and forth, the stronger it is, and the further away you get, the weaker it is, which is why when you have a magnet that's really far away from something, you don't notice it. And as it gets closer to something it's attracted to, usually another piece of ferrous metal, it'll get stronger and you can feel the pull until it finally touches it. And then you're like, whoa, you can really feel that strong connection between those fields. And then as you pull it away, it gets weaker and weaker and weaker. And so that is the principle behind electromagnetism. Now, we say it's everywhere, but where exactly is it in our life? Well, here's 3 things that we see every single day. This is a remote, much like our tinier version here that we use on our projectors. Remote controls usually have a little lamp at the end, like an LED, because it uses something called infrared, which is a wavelength in the red bandwidth, which we can't see. Once again, it's invisible, so we can't see this. And when we hit a button, it tells the device it's pointed at to do something, which is why if you hit a button, it'll work. And then if you put your hand over the front, you're blocking that frequency from going through, you're blocking that energy. It stops it from connecting and telling the device what it should be doing. Another one we have is a microwave, which uses microwave, hence the name. We have one right over there if you want to. Ta-da! And here's our microwave that we use in our little science lab here. And put your food in. There's a little thing up here that sends little microwaves out, and those cause the atoms in your food to vibrate, 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 and it heats it up. That action of the molecules and the vibrating back and forth like this and the atoms shaking causes heat, which is also why you'll see this mesh on the inside, because that wavelength is just bigger than this, so it can't escape, so it doesn't cook us. So if you're wondering how your food stays safe in there, and you get light out, but you don't get any radiation coming out of that could cook you, it's because of that mesh that protects us from those electromagnetic fields boom, coming out and causing us to get cooked. And another one, a phone, which is more than a phone nowadays. Everybody has a phone or a tablet that works on wireless fidelity. Well, that is called radio frequency. Just like radios from the old days, it just uses a different bandwidth. In other words, a different frequency, radio frequency, in order to connect. So when you have your phone on or your tablet on, it's sending electromagnetic fields all over the place, looking for devices to connect to, looking for antennas and things like that. So these are just 3 things we see commonly that use this. Pretty much everything that uses electricity gives off some sort of radiation, some sort of frequency that's in our world. And it's all invisible to the naked eye. Now, this is our planet. And now, if you remember, this is the biggest thing we've got that uses electromagnetism. In the center of our planet is an iron core. It's molten and it's twisting and it's got all these metals and stuff moving around in it. And it creates a giant magnet. So we live on a giant magnet. And that magnet has a field. Remember what I was telling you? Of electrons that are moving from one to the other. And all those are in the center. And just like as you see buses going down the road, all the electrons get on one bus, but some of them are left behind because there's more than can travel on that one in here. So then they go to the next one. And they go to the next one. And they're all trying to get around to the other side. And this is the funny thing about our planet, which is what I was explaining to Mr. Bones. All of our globes have the north up here and the south down here. You're like, but okay, that makes perfect sense, but its magnetic field is the opposite. And that's because we drew maps based on where we were at. Most of the maps started being drawn in Europe, and they put Europe in the north because that's where it started, and then they built all of the map based around those concepts. But in actuality, if you've ever been in Mr. Music's class when he has a globe that can flip, I always flip the globes upside down because I know that the actual magnetic north is in the south. So we're actually on the opposite side of where we should be. We should be in the South Pole and Australia should be in the North Pole, but that's just funny business. So all that field is being created and it helps to protect like an armor around us from solar radiation, from extra stuff from the sun which could harm us. And it helps to protect so that we keep our atmosphere inside of it. And it's just generally a good thing to have out there. It's the best thing around, and it's what allows us to live on this planet. But now we get to have some fun with it, because the whole purpose of this is we're through with simple machines, how physical things we can move in our physical world. Now let's start to think about more interesting machines, and I have a few out here. In fact, let's go over to this one, which is totally fun. Okay, so Mr. Bones, this is a really cool instrument because it's the only instrument in the world that you don't actually have to touch in order to play. So in the future, if you ever want an instrument that you're not supposed to be touching on, this is the one to go with. It's called a theremin. They are super cool. And what they use is electromagnetism to create a field that we can interact with physically without actually touching it. So normally it sits on a pole, and as I move my hand closer, I'm playing with the electromagnetic field that it's generating around it. And I'm just moving in that field. And you can hook this up to all sorts of other cool devices to get crazy sounds out of them. And yeah, these are a lot of fun. So if you ever want a kit project, work on something like this over the summer. All right, so today's experiment, we're going to be making our own compass so that we can check out that magnetic field that surrounds our Earth. So even us, with this tiny needle and this tiny magnet, can sense and detect and interrupt some of those electrons and some of that field that's being generated by those subatomic particles. So many subatomic particles moving from one side to the other side of our planet. So the first thing you're going to want to do is get a small needle. Usually the smaller the better. This is just a big one that we have here. A refrigerator magnet. Now this came off the back of something on a refrigerator. I would suggest if you have these kind with the tape magnet that's really thin, or like the one that's here, that might work, but it might not be as strong as a larger, thicker refrigerator style magnet. I have a compass here so we can see which way is north, and then I'm going to take my magnet, let me find the needle, and I want to make sure wherever the needle is at, that I'm constantly rubbing in the same way. And I want to make sure that I'm getting full contact with the needle on the magnet. And I'm not like doing this all over the place. I'm just dragging it all in the same direction, because what I'm trying to do is I'm trying to get electrons to rest on one side of the needle and not the other, so that this starts generating its own magnetic field. All right, so it should only take a few times, and always lift up, bring back, lift up and bring it, because I'm kind of scooching as many electrons to that surface as I can. And hopefully, if I get it right, we'll be able to find our magnetic north. All right, and now I'm going to take a piece of wood. If you have cork, that works really well, but it has to be real cork. It can't be like the plastic cork that comes out of some bottles. I'm gonna balance it on there, and hopefully it doesn't fall off when I set it in the water. Don't fall off. There. All right, now it's gonna have to settle and hope the surface tension doesn't mess with it too much. And let's see if it finds north. Oh, here, and I will try to move it. Let me move it a little bit just to see that if it's locked in there. Oh yeah, see, as I'm shifted around, it's definitely finding the north. And if I bring my compass over, my compass is, yep, we're looking at north, and there it is, we found it. So yeah, have fun with that experiment, and I hope it works for you. And remember, magnets have two sides, so make sure you're using the positive side to rub it, because when you put it in, it might reverse, and if it goes the other way, as long as it's lined up, that'll be facing magnetic north. Maybe not polar north, but magnetic north, and that is the lesson for today. So flip your globes upside down.